Okay, here we go. We're going to do, gotta find my little square here. We're doing 1993D, where we have two butane molecules. Why? We're going to mix that with 13 oxygen molecules. That will produce 8 carbon dioxide. Combustion reaction, yeah. Oh yeah, we remember these. And 10 waters in liquid state. Okay. It says the reaction represented above is spontaneous at 25 degrees Celsius. Assume that all reactants and their products are in standard state. So first it is asking us to predict the sign of delta S for the reaction and justify your prediction. So we're asked about delta S. Okay. So when we look at this, we see that the number of moles of gaseous products, we have 8. And on this time we have 13 plus 2, we have 15. So that's one reason to suggest a delta S that is negative. Or you could also say that a liquid is formed from its gaseous reactants, which also is a nut. So we're going to say delta S is negative due to a decrease in the number of moles of gaseous I'm not very good at spelling. Good enough. Gaseous products. Compared to that of the reactants. You could also say that a liquid is formed from gaseous reactants. That would also be a good, valid reason for a decrease. And like I said in the last example, there's a decrease, there are lower number of microstates for products versus reactants. So like I said, I never heard the term microstates, but since it's used in your book, and I've seen it in a couple more recent questions when looking over sample questions for AP problems, every once in a while they throw a new term in the book and they expect you to know that term, even though it's really not widely used in the world. Okay, so B. It says, what is the sign of delta G for the reaction? How would the sign and magnitude of delta G be affected by an increase of temperature to 50 degrees? Explain your answer. So first, they just want to talk to me about delta G. And then it says, how would both sign and magnitude be affected by increasing T to 50 degrees. So let's take a look. Okay, so for right now, delta is G is equal to, delta G is less than 0. That means it's negative. We know this because it's a spontaneous process, is described in the problem. It says the reaction above is spontaneous at 25 degrees. So this is true at 25 degrees C. And it's asking what happens to delta G at 50. Okay, and what we know for sure, we don't have any values again. Trust me, we will be doing problems where we're actually plugging in numbers, and you will be finding what temperature delta G changes from negative to positive, or when is it at 0, and what does that mean, etc. So what we're going to figure out, for what we can confidently say for now, is it becomes less negative as the temperature is increased. Because we're already saying delta S is negative, we know how it occurs spontaneously, so we can confidently say delta G is or delta H is negative. Because if it's occurring spontaneously and we're getting a decrease in entropy, then it must be coming from the only other factor, and that's the enthalpy. So, good. You could once again relate it to this equation. Delta G is equal to delta H minus T delta S. You could say this is negative. That means the negative, the contribution for T delta S increases at a higher temperature. Influence or magnitude or effect of a negative delta S increases at a higher temperature. There's lots of different ways to say it. Okay, I think that one's easy, does it? So let's move on to C. C says, what must the sign of delta H for the reaction, what must be the sign? We already did that. Okay, okay, so here, it must be negative. Delta H must be negative since the reaction occurs spontaneously and the value of delta S is negative. Yeah. And then it says, how does the total bond energy of the reactants compare to that of the products? Remember, bond energy is the one. What we're saying. So now we're going to take, okay, so remember, first of all, what's bond energy? Bond energy is the energy it takes to break the bonds. A bond between a chlorine and a chlorine, a triple bond in between a nitrogen, whatever bonds. We're talking about the bond, the energy it takes to pull off that pin cap. So the higher the bond energy, the more stable. Not to be confused with the whole idea of heat of formation, which is the lower energy, the more stable. Okay, here we go. We know that the bond energy is going to equal to the summation of the bond energy product or reactants minus the summation of the bond energy products. Okay, and it's saying the question exactly for the second part of part C was, how does the total bond energy of the reactants compare to that of the products? So they're trying to say, how much is this total value compared to here? So what we do know is, since delta H is less than 0, it's negative. Negative. I gotta change my pen. My fingers aren't working with my mouth. the bond energies of the reactants, right? This value minus this value. In order for this to be a negative number, this value has to be less than this. Agreed? So what they're saying is a reaction that the bond energy in all of these reactants have to be less than that of the products in order for it to be negative. It would look something like this. Bond energy reactants. That's the energy we put in. The energy we get out is the energy left. Okay, yeah. So this number, whatever it is going to be less than that number so that we get a negative number. So for example, this were 5. This could maybe be 10, and you see that we would get a negative 5 for an answer. Hopefully that's clear enough. Let's move on. The reaction, when the reactants are placed together in a container, no change is observed. So we know that we can have butane present in a container with oxygen. We have some experience with this with our lab, right? There's butane in here. And O2 can even be exposed to it, right? Under pressure or not. And we have these two things. And it's saying, when they're placed together in a container, no change is observed, even though the reaction is known to be spontaneous. Explain your observations. Just go for it here. We could say a lot of things. We could say, I know what the answer is, but you could say one thing, that the reaction is happening. Reaction may be happening, but just so slow that it is not detectable. That would be one thing. And it may be that is happening so slow that it's just not detectable. That could be very well true right now. If we can't detect it, how do we really know? I told you that diamonds aren't forever, that they do decompose. It's just their half-life is thousands and thousands of years, so we just don't care because we don't ever live that long. So there's one scenario. Another thing could be has an extremely high activation energy, E sub A. And this is when we did the diagrams like this. Right? Where we said, hey, the energy of the reactants like this, right? And then we would say, like, this is E sub A. This is energy it takes to actually break the bonds. So, and this may help explain. Let's relate. I think this is a good time to relate the binding energy to that of the regular enthalpy diagram, because I think this is a good idea. So remember, when we're talking about the binding energy, we're saying the reactants, let's even do this, we'll say are less than that of the products. So what we're really doing on this line, before we were saying delta H is here, right? And it still is. This is still delta H. This would be a negative value. How this diagram relates to bond energy is the energy it takes to break the bond. So it's from here to the top of the hill. So this is B, E, reactants. Right? And then this is the energy if we were going this way, right? Remember, we're not going this way, so we're not getting it back. We're comparing it to going back over this hill. Whatever it is, it's the energy it takes to break it. So this is the BE of the products, but it's going in reverse. We're not getting it back. It's not falling down. We're always going uphill for bond enthalpies. We're talking about the energy it takes to break the bonds. But you can see if we broke the bonds, boop, we'd be at the top of the hill. So heat of formation is the energy we get as we go down. Binding energy is the energy it takes as we go up. So hopefully that helps, because I think some people are always confused. Why are we subtracting now products from reactants and whatnot? But either way, this is the E sub A. So for the forward reaction, no matter which way, if we're going this way, it would be different, but the E sub A may be high. That could be another reason that you don't observe them happening. The energy it takes to break the bonds just is too much. Then that is available in the environment at that time. It could also say the catalyst might be. You could say you may need a catalyst or a spark. It's another way of saying we need a activation energy that's unsurmountable for what's available. Okay, I'm all done. Good luck. Good luck, or see you tomorrow.